So we started looking at this section last week. Uh, this is probably the last section, actually, as it turns out. And what it's all about is decoupling your kind of compute components using messaging. There are other ways of decoupling components as well. For example, there's something called an event bus, which is something that AWS has as well, but we won't get to look at it. So we're working our way through this set of slides here, and you can see I've revealed this lab. Now, this lab will span out over the next 3 weeks, I suppose. And it will, the good news is it's the last lab that you have to work on. You do have to submit this lab as well. Although, as I said, the submission won't be until about 3 weeks' time, but you can start working on the lab from today's lecture onwards. So let's get back to these slides here. And just to remind you, this is kind of this scenario where these messaging services are useful. So it's where you've got, let's say, a chain of, in our case, lambdas, because that's what we're mainly using it as our compute component. But just sticking with that, you've got a chain of lambdas, and these are what we would say they're tightly coupled. And I talked about, and we like to decouple them from one another. And I gave the reasons as to why we don't like this tight coupling. If you can avoid it, you try and avoid it. And the way you do that is you change your architecture from this approach to this approach. You stick in these intermediaries between the compute components, thus decoupling them. Now, for now, the way we're looking, or the way we're implementing, I suppose, this part of our architecture is using the SQS service, although it's not the only way you can do it. And the way it works then is this lambda component, it writes messages now to what we call a queue in SQS terms. And this lambda here, it's not the queue doesn't push the messages to this lambda. Instead, this lambda periodically polls the queue, asking it for messages. The queue then will return a batch of messages back to this lambda, and it processes them. And also the lambda, directly or indirectly, the lambda is responsible for, once it has processed the batch of messages it has received, it is responsible for asking the queue to now delete those messages from its store, if you like. So that's just the basics of how it works. So if we push on to where we actually started to look at an example of this, which was here. So in this simple example, we're using the AWS CLI as what we call our producer in SQS terminology. Producer is the entity that is writing messages to the queue. So the CLI is writing or sending messages to the SQS service, really, and the SQS service puts them into the queue. And on the right, then we have our Lambda consumer. And as I explained the last day, the Lambda doesn't directly talk to SQS. Instead, it's the Lambda service. It takes care of polling SQS, asking it for messages from a particular queue. SQS responds, presumably with a batch if there are any. Otherwise, it responds with there are no entries or there are no messages. If it does respond with a batch of messages, then the Lambda service, it actually invokes your or calls your Lambda function, passing it, as always, passing it an event object, but that event object contains within it the messages that were received from SQS. And I demoed that the last day to you. Typically, the messages that are sent to a queue, typically they're in JSON format. They don't have to be though. They can be in any format, XML or whatever. Um, but if they are in JSON format, or indeed if they're in XML format, SQS serializes them or stringifies them. And it's that serialized form is what our Lambda function will receive. So you just need to be aware of that fact, and you do need to parse the messages before it can actually process them. So we had all of this the last day, really. Okay, let's just push on to here. This is kind of where I left off. Now, uh, uh, Lambda, when your consumer is a Lambda function, fortunately, the Lambda service will take care of scaling issues for you. And what we mean by that is, so the Lambda service is polling SQS for messages. Now, if there are a lot of messages in there, right, that means every time it polls it, it's going to get a batch of messages. I think the batches are always of size 10. Either way, there's a high volume of messages being received by the Lambda service. Now, in order to deal with that high volume, what it actually does automatically is it creates duplicate uh, running instances of your Lambda consumer. And in other words, it creates multiple micro VMs and loads each of those micro VMs with your single Lambda consumer. So, and it runs these kind of in parallel. And so the batch of messages that it receives, so again, Lambda service polls SQS, gets back a batch of messages. Let's assume there are 10 messages in the batch. It will actually split that batch up into sub batches, and it will, distribute the sub batches to these parallel running instances of your Lambda. So the Lambda service takes care of kind of scaling up the number of instances of the Lambda function that it needs to deal with the volume of messages. And that's what I'm talking about down here. Now, to try and demonstrate, sorry, before I say that, um, based on the documentation, what I've read is that it automatically creates 5 instances, parallel instances. Now, sometimes it does, sometimes it doesn't. Um, uh, Sorry, what I was going to say there is initially it kind of creates 5 parallel instances of your Lambda function, parallel executable instances. But from there on, like it actually keeps scaling up. And I'm talking about here that I'm saying it adds up to 60 functions per minute. In other words, 60 creates 60 micro VMs per minute. That's the degree to which it can scale up if there is a really high volume of messages for consumption. You can control how frequently the Lambda service polls SQS, but typically it's kind of polling it every, number of seconds. And so if it's getting a full batch of 10 messages every single time, then it will keep on scaling up your parallel instances of your Lambda consumer. And this is the rate at which it scales up. Okay. So the scale up to 60 functions per minute, up to a maximum of 1,000 It'll never go beyond 1,000 parallel instances of your function. And you might remember that magic number of 1,000 that actually is relates back to when we were talking about the Lambdas uh, service earlier on in the semester. The AWS people arbitrarily have decided that no AWS account can have more than 1,000 Lambda functions running at any one time. They don't all have to be the same function, but just the total number, essentially the total number of micro VMs, irrespective of what that micro VM is executing inside it. You cannot have more than 1,000 micro VMs running on your account at any particular point in time. So that's where the 1,000 kind of comes from. Uh, so clearly, it scales up to a very high degree to deal with very high volumes, a very high throughput of messages. Now, just to try and illustrate this parallel stuff that's going on, um, here's a little system that I've will demo to you. So on the left, I've got a Lambda, and really the only purpose of this Lambda is to generate messages to write to SQS. So I'm calling it a kind of a test harness to demonstrate this scaling. The scaling happens over here on the right. So this generate orders is going to be sending messages to SQS, and this Lambda here is going to be processing those messages, those orders, Maria. All I'm saying down here is this Lambda is communicating directly with SQS, so it needs permission to do that. And the way you do it is it's very similar to the way we give a Lambda the permission to read and write to a DynamoDB database. So in the CDK world, there's this convenience function available to us that we can invoke on a Lambda function, sorry, on the queue. We can invoke it on the queue and pass it a reference to your Lambda function. And that essentially then will cause the CDK via the CloudFormation service to generate the necessary IAM policy and attach it to this function to allow it to write or send messages to SQS. You might remember, this is a bit off topic now, but you might remember the last day when I looked at, sorry, if I go back to this, sorry, uh, back to this example that we had the last day. When we looked at the code for this Lambda, it wasn't communicating directly with SQS because, well, it just isn't. That's just the way it works. The Lambda service, it actually calls the Lambda function and it passes it the messages within the event object. So this Lambda doesn't communicate directly with SQS at all. It still needs the permissions though, in order to allow the Lambda service to poll SQS on its behalf. And I talked about that the last day. But just in this second demo, in this demo, this Lambda is going to be communicating directly with SQS. And so it's going to need to create an SQS client internally and talk to it. And that's why we need this explicit statement in our CloudFormation, in our CDK code to grant permission to this function, to send messages to SQS. So I've already deployed this application, and I'm just going to step through parts of the code. So this is it here. I'm actually going to go down to here first in my types declaration file. So I've just declared an order type for myself. Very simple, yeah. And I've also created a bad order type because we'll need that in a while. We don't need it right now, but we will need it for another uh, aspect of SQS that I need to demonstrate. And I've just decided to use the utility, the partial utility type you might remember this utility, this TypeScript utility type will make every property of this structure optional. So these will all be optional in a bad order. Uh, the idea in my mind anyway is that all of these properties are actually essential. So if our consumer receives an order that is missing, I just decided arbitrarily for it to check that the um, no, I think I actually get it to validate the structure of each order. And if it doesn't match this structure, then I get the consumer to throw an exception. Uh, the issue then is what happens to that exception. Now, I don't want to talk about that side of it yet, though, but just to cover it. And then I have an order mix type, and an order mix is either an order or a bad order. Okay, so there are my data types. If I go into this Lambda here, this is the Lambda that is going to generate messages. It's kind of my test harness. This is just pure code, really. Here I'm getting a reference to, um, sorry, I'm creating an SQS client using the SQS SDK. And I'm doing that outside the handler itself. In other words, this is part of the initialization code for this Lambda function. Here I'm just creating an array of orders. So I'm creating 10 orders for myself. And just to make it easier for us to see what's happening on the consumer side, each order will have a customer name of the form user and then a number. So it'll be user 0, user 1, user 2. Yeah. We don't really care about the address or the items in the order. Okay, so that's my 10 orders. So I've put all of that code in the initialization part. And here's the actual Lambda itself. Remember now, this is the Lambda that's sending messages to the queue. There are two ways that you can send messages to an SQS queue. You can send, if you've got a number of messages that you want to send, which in our case we do because we want to send all of the 10 orders to SQS, you can actually send a batch of messages. There is an upper limit of 10 though to the batch, which is really why I picked 10 there. Or you can send the messages individually. Now, just for convenience, I'm sending the messages as a batch to SQS. And um, the other thing I want to just mention is so far the only other service that we have interacted with from Lambda was DynamoDB. And you might remember the way the DynamoDB SDK programming model is designed. It's all about creating commands and then sending those commands to the DynamoDB service. Now, the SQS SDK follows the exact same pattern. And that was obviously a conscious decision made by the AWS people to make it easier for us as developers to understand the programming model. So in the world of SQS, we have things like send message batch command. There's also a send message command when you want to send an individual message. Okay, so it's all based on commands and sending commands to SQS. So that if I go down here now into the body of my handler, um, I first of all, in order to use that send message batch command, I first of all need to create a send message, what's it called? Send message batch request entity. Okay, a bit of a mouthful. I need to create one of those for each message in my batch. So that's why I've got an array of them here. And all I'm doing is I'm mapping over my array of orders, the array of orders that I've created up here. I'm mapping over them, and each each message has to have a unique identifier. And I'm just using a third-party library, the V4 library. What that does for me is it called a V4 or is it called something else? Oh no, sorry, the library is called the UUID library, and it has a method called V4. And what V4 will do is it will essentially generate a a random number, kind of a bit like a hash value, really, which we can guarantee will be unique. So I'm just using that to generate the ID of my messages for me. I don't really use the message ID, but SQS requires each message to have its own unique ID. And message body then is just one of my orders in stringified form. Okay, so I've got an array of these things. And here we go, we create our send message batch command input. We put that stuff into it. We need to specify what queue, SQS queue, we're sending it to. I haven't shown you the CDK code yet, but in my CDK code, I create my queue, and I'm essentially passing a reference to that queue into this Lambda. And eventually then I am sending my batch command to SQS via the SQS client. That's all that's going on there. In the commented out code down here, I'm just showing you how, if you wanted to send one message, this is how you would do it. So there's a structure called what's it called? There's a send message command as opposed to send batch message command. And this is what you have to pass it. You have to pass it the message and just the name of the queue. You don't have to give the messages unique identifiers. In this case, SQS will take care of it. But I've that commented out because we don't use it. Okay, so that's the code for this guy here. Now let's look at, we'll look at maybe the CDK maybe next. No real surprises in there though, when I think about it. Okay, so we create our orders queue. Not that it's that important, but you can control. Remember we said that SQS will persist the messages in the queue for a maximum of 14 days. That's just in case no consumer happens to contact it within a shorter period of time, looking for messages. So I've just arbitrarily, I mean, I could have left the default. I'm not sure what the default retention period is, but I've fixed it at 5 minutes. The stuff that I've commented out here, we can ignore for now. This is the Lambda that's my consumer. This is the Lambda that's generating the messages. And you can see here, I'm passing down the queue URL. A queue, SQS generates a URL for a queue, which means really we can invoke it from anywhere. We don't have to invoke it from within AWS. And as I'm on that, right, in the consumer, this Lambda here, I'm not passing it a reference to the SQS queue at all. And that kind of reinforces the point I was making there that the consumer, the Lambda consumer doesn't talk to SQS directly. Okay, and here is, we've seen this from last week. This is how we still need to associate SQS as being the event source for my consumer, and that's what I'm doing there. We saw that the last day though. This is where I'm giving my test harness the permission to write or send messages to SQS. And that's it, right? And I'm outputting I'm outputting uh, the name of the generate orders function because I will be triggering that from the CLI. And on the consumer side, which is here, doesn't do anything really interesting for now anyway. It just console logs the event. Well, it does maybe something slightly interesting. We always get a batch of messages, even if there's only one message in the batch, it's still a batch. How do you get access to the batch? It's in a property called records within the event. I showed you that the last day. So records is going to be an array structure, which is why I'm looping over it. And each entry in that array, uh, we're just trying to access the body property within the array entry, and the body property will contain the actual message itself, albeit in serialized or stringified form, which is why I'm parsing it. And then I console, we can ignore this stuff for now. Okay. Um, I console log the message. Okay, so really the only two lines that we're interested in this for loop is the fact that we have to parse it and we're console logging it. All of my orders are going to be valid, so this if statement is going to be uh, false in each case, so it never comes in here. Right, so I have deployed the stack, and what I need to do now is I need to trigger the generate orders lambda and see what happens then on the consumer side. And you can't really predict, but it's certainly going to create more than one instance of my consumer lambda. Um, how many parallel instances it creates can depend on a number of variables, really, not just the number of messages. It can also depend on, how busy the actual server where my lambda is running on is at any particular point in time, and we can't really control that. So let's just see anyway what happens. So I make sure my logs are clean. So the lambda name, don't know if you can see that now on your side. Let me just. So I played a little bit with this earlier on. So I'm just doing AWS Lambda, invoking the Lambda. This is the name of the generate orders Lambda. So I would just go return. Okay, and if I go switch over to here and do a refresh. Now, because the only log group that's appearing is the log group for the generate orders, and the log group for the processed orders won't appear until after a slight delay, and that's because of the polling that's happening on the consumer side. So you have to wait a couple of seconds until you see the log group for your consuming lambdas. So if I refresh, I now have my two log streams. Uh, let's see what happens. So this is the log stream for the consumer. Yikes, created a lot of streams. Wow. Are they all? Okay, that looks interesting. So this is 1246, 645. This one here, that's an old log stream from when I ran it, I think earlier on. So it looks like the 1246 streams are the ones that are relevant. So it looks like there were one, two, three, four, four streams created, which means there were four Lambda parallel instances of my Lambda uh, executed. Now, if we look at the detail again, so let's look at this log stream here. So again, because I've got four log streams, that means I have four parallel instances of my consumer function. Four micro VMs, if you like, were spun up by the Lambda service. And so we need to see which messages, which orders were sent to which uh, Lambda instance. So let's look at them from the top down. And I can see here that order number 9, well, sorry, order number 10, because it goes from 0 to 9. Order number 10 and order number 3 were sent to one of the Lambda instances. Okay, let's look at another one. This one received order number 4 and order number 7 and order number 8 and order number 5. So it got four of them. So I think we've got 6 so far. How many did this one get? This got 2 and does it all add up? This one. This got 2 as well. So that I think adds up. We had 3 of them getting 2 and 1 getting 4. So that makes 10 in total. Okay, so that's by outputting the user number, that just makes it easier for me to work out which orders or which. Okay, so in summary, 10 orders were sent, 10 messages were sent into my queue. The Lambda service polled it. It got all of the 10 in the batch that it received, and it decided to spin up 4 micro VMs, each running the same consumer Lambda, and it split the batch of 10 into one group of 4 and 3 groups of 2, and it passed them within the event object to each of these 4 uh, running instances. The other streams, as I'm saying, because if you look at the timestamp on them, they're from about over an hour ago, so they were from an earlier. Sometimes it's a bit. Sometimes, even though you might delete a log group, the log streams can sometimes still remain. That's why we're looking at old log streams here, even though when we looked at the log groups initially, there were no log groups. Are there any questions about that so far? So the point we're demonstrating is the idea that the Lambda service would scale up the number of parallel instances of your consumer Lambda as it needs, depending on the volume of messages it receives. Right. Um, so we've seen all of that and that. Yeah, so this screenshot was just from when I ran it previously. And in this particular example, again, there were 1, 2, 3, 4. There were actually five log streams created. Uh, and when we looked at I looked, the screenshot shows you just one log stream. Oh yeah, I mean, in as well, something we mentioned about SQS was that you're not guaranteed that the order of the messages is the same as the order in which they were written. Now, okay, we sent a batch, but presumably the batch of messages start from the first entry in my array of orders, right? True. But the order in which the messages are received by any particular consumer instance is completely unpredictable. There's no guarantee of the order. And we saw that in the demo when I looked at the log streams there. They can be in any order at all. So if you require the messages to be in the order in which they were written, you have to configure your queue to guarantee that. That does have impacts though, or that impacts on the performance of your SQS service. Now, so it created four parallel instances there, but maybe we don't really want it. It didn't really need to do that. I mean, potentially it could have sent all of the messages because there was very little processing going on. It could have sent all of the messages in my batch of 10. Maybe not to one consumer, but maybe two would have been sufficient. And there was no real need to scale up at all. And maybe the natural rate at which orders are generated in my application, if it was a real life application, the rate at which orders are being generated and sent to my queue is such that I never really need the Lambda service to have more than, whatever I decide, let's say two parallel instances of the consumer running. So you can actually control that. And that's what I'm illustrating it here. So in the actual consumer, when you create a link between the consumer function and your queue, and that's what we're doing here, there's a property called the max concurrency property. And you can set that to any value you want to. You cannot set it to one. It actually doesn't allow you to set it to one. The minimum is two, but you can set it to two or anything above that. And so if I just quickly do that, before we do that, I just do a cleanup. I always think it's a good idea to clean out your log streams fairly regularly, just to make sure you're not looking at an old log stream, especially if you're debugging. Notwithstanding the comment I made now that even sometimes when you delete a log group, some of the log streams associated with a group tend to hang around a little bit, so you do need to still check the timestamps on it. Uh, so in the CDK, you go to where you're connecting up your consumer with your queue, which is here, and you set the maximum concurrency property. Just as a matter of interest. Okay, there's no, all it's telling me here is that there's no default value. Uh, but I think the Lambda service itself defaults to, sorry, no, it doesn't. There is no default value. Anyway, so I've set it to two explicitly. Now, if I trigger the whole process again, so I run my test harness, my generate orders Lambda. Sorry, before I do that, I need to redeploy, don't I? And it's the function is going to have the same function name, so I don't need to go checking my function name. The same, actually, by the way, when you're using API gateway and the you get a URL for your gateway, even if you make some configuration changes, it's going to be the same URL for the gateway all the time. So I can just straight away, I can now trigger my generate orders Lambda. And so my prediction here now is that there will definitely only be two log streams for the consumer Lambda. So it hasn't, the Lambda service hasn't polled SQS yet. It's polled it now. And let's just do a refresh to hopefully to clean up all of those. Okay, and here we go. There are actually only two log streams, which means there are two instances, two micro VMs were only created. And just for the heck of it, let's look at the detail. So this got user one, gosh, you don't, sorry, user 8 and user 1. So that must mean the other Lambda got the other 8 orders. Okay, now what happened here? So we got 1, 2, 3, 3, and 4, 5, 6, 7, 8. Now, what happened here though? Uh, this is something I could have explained when we started talking about Lambda and log streams. So the way we interpret this log stream here now, or any log stream for a Lambda, the init part of the log stream relates to the running of the initialization code within your Lambda. Okay. The start is the log part of the log stream that relates to the running of the handler itself, the function itself. The other parts of the stream then are based on how many console log messages you have within the Lambda. So we had a console log at the very beginning, which is this part of the stream here. And we had a console log inside in our for loop. And so because this is processing two orders, that's what those two parts of the stream are about. Three orders, sorry. Three orders, yeah. So with that, those three there. End is clearly the end of the execution of my Lambda. Now report, okay, that always you get that part of the stream after the end. And what actually happened here is the Lambda service reused this particular micro VM. And in other words, the micro VM has already, as we say, it has already been warmed up. It's no longer a cold micro VM. It's a warm micro VM. By that we mean the initialization code has been executed and it only needs to be executed once. So it doesn't re-execute the initialization code because we don't see the init part of the log stream, this part here. We don't see that again down here. Now, really what we should have seen next is start, but this part of the stream here is the console log for the second execution of my Lambda function within the same micro VM. Really, that start there should have appear up here before it. That's something that you can get with log streams, that sometimes the ordering of the entries in the log stream may not always be the order in which they were executed. That's just something that's just really as a result of the fact that these log streams are being sent across a network. So sometimes they're slightly out of order. So strictly speaking, this actually happened first, and then this happened. So the start, as we know, is the start of the execution of the Lambda function. Uh, these console logs are from the body of my Lambda function, the Lambda completed, the the Lambda service reused this micro VM for a third time. It executes my Lambda function for a third time, which is what the start is. And this entry here and these here are within the body of my Lambda, and that's it. It finishes. So although there were only two micro VMs created, the Lambda service reused one of those micro VMs 3 times. The other micro VM, it only used it once. Okay. Uh, Now, why it decided to do that rather than split the 10 orders up into, I don't know, 2 5s or a 4 and a 6, and just give 4 orders to one instance of my Lambda and get it to process all 4, and give 6 to another instance of my Lambda and get it to process all 6, is completely arbitrary. Instead of taking that approach, it still broke my 10 orders up into 4 batches, and it reused one of my lambdas 3 times, as I've been talking my way through there. So, you can't really control how it splits your batch of messages up into sub batches. All you can control are how many parallel micro VMs does it actually uh, create to process a batch of messages. And if I ran it a third time, just for the heck of it, we'll see what happens. Do a cleanup again. There are only going to be 2 parallel micro VMs. Did I clean those out? Sorry, no. Don't think I did actually. Sorry, let's just do that again. No. Sure, what's going on there? Manual refresh. Okay, so we've got two parallel instances, 1306. And for this one, okay, it's give it 1, 2, 3, 4 orders. And for the other one, okay, that's a little bit cleaner. It gave it 1, 2, 3, 4, 5, 6. So again, completely different sub-batching um, approach in this case. This is the one we're looking at now, actually is a bit more natural. And again, just to go back to the log stream, well, again, the log stream is slightly out of order. The very first entry in the log stream should be the init entry, which happens to be, is it appearing at all? There has to be an init. There's no init. It may be that this log stream is actually reusing the, sorry, that this log stream is coming from the micro VM that it already had from the previous execution. It just held on to it for a little bit longer because there's no initialization code running. In the initialization code is where we create our SQS client. Yeah, if you remember, if we go back to here, uh, we create an SQS client and we definitely need that. We create our array of orders. We definitely need that. So that has to execute, even though when I look at the log stream, uh, I don't see it in the log stream. Now that either means that, the log stream that was being sent by the Lambda service to CloudWatch, you know, some part of it just got lost along the network, or it's reusing the same micro VM from an earlier execution, and so it will still have the connection to the SQS service, and it will still have my array of 10 orders. But aside from that, you know, the sub batching is quite nice in this case. Okay, we spent enough time on that. Are there any questions, I wonder? No? Okay. Now, so when a consumer, it's always the Lambda service in our case, but as I've mentioned to you before, the SQS service was created long before the Lambda service existed. And the original use case for SQS was, well, in fact, the very original case was when customers had their own applications running on their own on-premise servers, and they wanted applications to be able to talk to one another for talk to applications of other customers or clients, if you like. Um, that was the original use case. Then it started to get used by EC2, where you were running an application on EC2 and it was using SQS either to talk to an application running on another EC2 or to talk to an application that wasn't running on AWS at all. And it's still possible, to have an application that is not running on AWS at all. You can still use the SQS service and it can still use SQS queues because all it needs is the SQS SDK, which is just a library, and it needs the URL of the queue, irrespective of whether you're a consumer or a producer. Now, um, back to message visibility too. So when a consumer polls SQS and the SQS gives it a batch of messages, maximum of 10, it doesn't delete those messages from the queue. It leaves them in the queue. but it sets what's called a visibility timeout timer for that batch of messages. I think it should really be called the message invisibility timeout, but it's called the message visibility timeout. And that timeout, um, what it means is that that batch of messages cannot be seen by any other consumer. Should another consumer come along and ask SQS for messages from the same queue, it won't be given the messages that it gave to the first consumer because their visibility timeout is still hasn't expired yet. When the visibility timeout of a batch of messages expires, then those messages are now available to be consumed by any other consumer or the same consumer that tried to process them the first time. But they're now visible, if you like. So this is again, this is a throwback to the very original days of SQS. So this message visibility timeout is a timer that is set once a batch of messages has been sent to a consumer. And I'm saying here it's set to 30 seconds, I think. Yeah, well, sorry, that's the default is 30 seconds. You can actually configure that. So let's suppose it is 30 seconds. For the 30-second period, if another consumer happens to come along and request a batch of messages, it will not receive the batch that it has sent to the first consumer. Once the timeout expires, that batch of messages is now available to any other consumer that happens to poll SQS. So that means that the consumer that did receive the batch of messages, it must process that batch and here's the important part, and it must tell SQS to explicitly delete that batch. It must do that within the 30-second period or whatever the visibility timeout period is set to. Okay, so the consumer must process and delete, as I'm saying here, a batch within that timeout period. Otherwise, the timeout will expire and the messages will become visible again. And just the image kind of illustrates this idea. So the timeout is something that you configure, and it's something that you would tune as you're testing your application to set it to, an appropriate value. Because if I'm saying down here, if you set the visibility timeout period to be too long a period, then that would mean that there will be messages inside your queue which could be processed by another consumer, but the other consumer can't get at them because the timeout period is still hasn't expired. Alternatively, if you set the visibility timeout to be too low a value, then it's possible that you can have more than one consumer processing the same message, and you clearly don't want that either. Now, I did say to you, even though we don't have an example of it, you can have multiple consumers consuming from the same queue. What SQS will guarantee is that, well, via this message visibility technique, is that if it gives the messages to one consumer, provided that consumer can process the messages and delete them within the timeout period, then SQS will guarantee that those messages will not be delivered to another consumer. Okay, so it's a tuning thing anyway. Now, that kind of leads on to this notion of a dead letter queue idea. And if I could just go back for a second to an earlier slide, way back to here. Where's my slide? Yeah. So this is where this is where we're not using queues now at all. So client sends messages to this Lambda, and we know how all of this works. Now, let's supposing this Lambda here throws an exception because as it's processing the message that it has received, there's something wrong with it and it throws an exception. Given that we've got a synchronous connection here, that exception will be thrown back to this Lambda. Now, you either program this Lambda to deal with that exception. If you haven't programmed it to deal with it, then it will throw the exception as a response back to your client. And again, either the client is programmed to deal with it or the client is actually going to crash. So that's fine when you've got this kind of synchronous communication going on. If any compute component throws an exception for whatever reason, then eventually that exception will bubble its way right back to the client, and you as the developer or user will know about the fact that the exception occurred, and you then start your debugging to find out, why did it happen, and you program to prevent it from happening, whatever the cause of the exception was. The exception could be that it was a bad message, and then you start investigating why did the client send a bad message and all of that kind of stuff. Now, the problem is though, when we start decoupling these components, in other words, when we get to here, excuse me, the problem now is if this Lambda throws an exception as it's processing a message, uh, this Lambda is never going to find out about it. Uh, and so really the exception is just going to die, and nobody's going to actually know about it or handle it programmatically. You would know about it, I suppose, if you really start monitoring your queue and monitoring your Lambda. But we'd like the fact that when this throws an exception, we'd like to have some programmatic way of catching that exception and dealing with it. And that's where this notion of a dead letter queue comes in. So these DLQs are really to handle exception or failure cases within this kind of architecture. So let's get back to that slide. So on the right here, I'm showing you that like if you didn't have dead letter queues, then what would be happening is your consumer, whatever it is, whether it's Lambda or EC2 or doesn't really matter, your consumer is polling SQS for messages, gets a batch of messages. As it's processing the batch, it throws an exception. Now, that will mean that the visibility timeout for that batch is going to expire. And so the messages, will be received a second time by this consumer because it's going to poll it again for more messages. It'll receive a batch of messages that may still contain the faulty one or ones that were in the first batch. And this is going to keep on happening. It's going to keep throwing exception. The visibility timeout of that batch is going to expire, and it's going to keep receiving the same batch of messages over and over again. And clearly we don't want that. Now, where the dead letter queue comes in is you can configure your queue, this queue here, such that if the visibility timeout expires a certain number of times, then that batch of messages should be sent to another queue, deleted from this one, sent to another queue. And what you do with the messages in that queue then is, it's up to you, the application developer. Presumably you would actually have another consumer here that deals with the messages in this queue. And this consumer, knows that what it's actually handling are error cases. That depends what you do in the error cases, depends on the nature of the messages and the application, et cetera, et cetera. But what you have with this DLQ is a kind of formal way of handling exceptions or errors or failures in your kind of main queue, if you like. This maximum receive threshold, this is the value that you can configure, and essentially it determines how many times are you going to allow SQS to send the same batch back to the consumer. You may actually want SQS to send the same batch to your consumer two times or three times, because maybe the reason the consumer is throwing an exception, it's not an exception. It may actually be timing out. It can't process the messages within a certain time period. Certainly, if this was a Lambda, when you've got a Lambda, you can control what the timeout period for your Lambda is. In other words, how long will the Lambda service allow that Lambda to continue executing before the Lambda service actually interrupts it. That's a setting you might remember that we can control. And so, you may actually want to allow your Lambda to have more than one go at processing a batch of messages. Because again, this Lambda is running on top of hardware, and maybe that hardware happens to be running lots of other Lambdas and maybe EC2 instances, et cetera, et cetera. But its available compute time might vary from time to time. So that's why you may actually want your Lambda, if your Lambda is the consumer, to have more than one go at processing a batch. So that's what this maximum receive count controls. Now in our case, we'll just set it to one, which means that we're only going to give our Lambda one chance to process a batch of messages. And if it fails, then that batch is going to be sent over to a dead letter queue. Um, Okay, so these DLQs really are all about kind of debugging error cases, whether they occur naturally or they may be as a result of some bad programming in your consumer that you need to fix. So to illustrate it, we'll stick with the same demonstration. And what I've done is I've put a bad order in my batch of orders. And what I want this is Lambda to do is once it finds a bad order, it's going to explicitly throw an exception, which will result in the batch of messages finishing up being sent to this queue, and the SQS service will take care of that. And I've got another Lambda then that's dealing with the bad order batches. Now, at the moment, this Lambda just doesn't do anything. It just console logs the batch of messages that it received from this queue. Okay, so that's the scenario. And we'll deal with we'll use the same stack. Now I need to make some changes to my stack though. So the first thing is I need a second queue. Which is here. And I'm just going to move that up. Okay, so this is my queue for taking batches of bad orders, as I'm calling it. Now, the way I make this queue, the dead letter queue for this queue, is by changing this configuration setting here. Isn't it like there now? Oh, yeah. How many mistakes am I going to make? So the dead letter Q is just referring to the Q up here, and this property here that controls how many times you're allowing the consumer to receive the same faulty batch. And so I've set it to one. That's what I was saying about the maximum receive count. So this property here, that's what I'm setting to one. And as I said, SQS takes care of, shifting the messages from one queue to another, provided you've set this configuration for it. You've told it about it. And as well, I just need a Lambda to handle that second queue. So here's my Lambda, I think. Here it is here. Move that up to where the other lambdas are. Doesn't really matter in general the order in which you put your code in a CDK file, but makes sense to put all the lambdas together and the queues together, etc. Okay, so that's just this lambda is just an ordinary queue consumer, just like this one here is. And the final thing is to make that DLQ to kind of hook it up to the lambda, which is what I'm doing here. And I may as well put those together as well. Okay, quick refresh. This is my dead letter queue. This is my main queue. This is the lambda for processing the dead letter queue. This is the lambda for processing the main queue. This is the lambda for generating my orders. Here I'm connecting up my dead letter queue to the lambda. In other words, I'm making it the dead letter queue the event source for my lambda. Similarly here, and that's it. CDK deploy that. Well, actually, sorry. I'm going to say no to that because I need to make some changes to I need to make some changes here as well. And so what I've done is just this, right? If I enable this piece of code, I'm just slicing in a bad order into my orders array here. And so this order has a customer name, it has items, but it doesn't have a customer address. Yeah. And I can now do my deploy, I think. And so if I look at this lambda here, this is the lambda that's processing my batch of orders. And I'm using the AJV library, which you're familiar with, to validate the structure of my orders. You can see here I'm checking to see within my for loop, I'm checking to see is the order a valid order? And so that's going to fail for that one invalid order that I put into the array of orders, and I'm throwing an exception. Am I throwing an exception? Oh yeah, I'm throwing an exception. So that will cause, so by throwing an exception, that will uh, that will mean that the Lambda service will not tell the SQSQ to delete the messages, to delete the batch, because the batch hasn't been processed properly, which means that the visibility timeout for the batch of orders in my main queue will expire. And because I've configured the main queue to remove a batch that was not processed on one attempt, remove that batch and put it into the dead letter queue. That's what should happen. Okay, so just clean up my log streams. If I just go back to the slides, what I'm documenting, sorry, now where are we? Oh yeah, that's okay. That's okay. That's okay. What I'm just documenting on this slide here is when I ran this particular application myself offline, if you like, I just recorded exactly what happened. Now, it won't be the exact same in this case, but here's the configuration that I had set up for the execution that I carried out. I set the maximum concurrency for the process orders uh, function. That's the kind of the main queue consumer. I set that to 2. Okay, so there can't be more than 2 parallel micro VMs of my process orders Lambda running. That's fine. I set the maximum receive count of the main queue to 1. And I explained what that means. I then ran I should comment as well that I set the maximum concurrency for for the Lambda that's processing the bad queue, the DLQ. Sorry, know about this. The maximum concurrency for this is set to 2. The maximum concurrency for this is set to 2. The maximum receive count for this queue is set to 1. So that's my configuration. My array of orders has 10 orders, and one of the orders is a bad order. And so when I ran it, sorry now, the other thing I should have told you, I guess, is if I go back to here, the bad order has a user called user X. Okay, so that'll, when I look at the console log from my Lambdas, wherever I see user X, I know that's the bad order. But when I ran it, this is what happened. Okay. So remember now there are 2 micro VMs running my processed orders. One of the micro VMs, it received the order for user 0, user 4, user 7, user 9. The other micro VM that was running processed orders received user 1, a batch consisting of user 1, user 2, user 3, user 5, user X, and user 8. So this sub batch here, this sub batch uh, that sub batch is going to be sent to the dead letter queue. This batch up here won't be because, it was processed fine. So this sub batch is going to be sent to the dead letter queue, which means that the Lambda that's processing messages from the dead letter queue, which I've called the bad orders Lambda, it also had two micro VM instances created by the Lambda service because I set the maximum concurrency to 2. And so this batch here is going to be was split up into two sub batches. One of the sub batches consisted of user 1, user 7, and user 8. User 1, user user 1, sorry, user 1, user 3, and user 8. And the other sub batch contained the user X order in it. Now, um, when I say that the bad orders function, given that the way I've kind of designed this, or maybe badly designed this, the bad orders function, it will receive orders that are still good orders. Because the only bad order in this case is the user X order. So I guess strictly speaking, this second lambda, the lambda that's processing the bad order batches, it should really go through the batch of messages that it receives, and if it's not a bad order, it should put that order back into the main queue. So this order here and this one, they should really be put back into the main queue so that process orders can actually fully process them. Similarly, user 2, that order should be put back into the main queue, and user 5. What it does with user X then, it really depends on how you want to handle that. So the point I guess I'm trying to make is that given the way I've designed this, my bad orders Lambda is actually going to be receiving orders that are still valid ones. They just happen to be contained within a batch that included a bad order. Yep. Okay. So let's just see what happened when did I run it? No, I didn't yet. Let's trigger it. Deployment is done. Run my Lambda that generates the bad orders and put them into SQS. Now, it's going to take a while for the log stream related to the bad order Lambda to appear. Okay, no matter how many times I refresh now, it's that there will need to be 3 log groups because I've got 3 Lambdas. It'll eventually come through, hopefully. Unless I did something wrong. Give it one more go. Okay, there we go. So let's look at the log stream for just processing the main queue, which is this one. Then there should only be 2 log streams because I set the maximum concurrency to 2. Looks like it didn't work. Why is there only 1 log stream there? Am I looking at the right? Let me check the code again. max concurrency is 2 for that one, and the max concurrency for this one is 2. Shouldn't be 2 log streams. Well, it's a maximum of 2, maybe. Let's just see what the log stream actually looks like. Again, we've got a case where it seemed to use the same micro VM and used it twice. So it did that rather than creating 2 parallel micro VMs. Okay, it's just uh, another scenario, I guess. So anyway, this first execution, user 8, 0, 1, 2, 3, 5, and 7. It looks good. And for the second execution, 4, and it hit X, and it threw an exception, which we can see here. So what I would expect is when I look at the failed orders Lambda, look at the log streams for that Lambda, I should see that it's trying to process this order and user 4. So we got lucky this time. There was only a batch just containing 2 orders. So there's only one good order that should be put back into the queue. So let's look at the other the other log group. Which is this guy here. Seems to have done a similar. Oh, sorry. Um, sorry, user, let's see. There's user 4 and user X. The reason user 9 is appearing in this log stream is because in the log stream that of the process orders that included user X, that log stream, or sorry, that batch of orders also had user 9 in it. The reason we didn't see user 9 though is because the user 9 order came after the user X order in the batch that the Lambda was processing, and it's once it hit the user X order, it threw an exception, so it never got to process the remaining orders in that sub batch. And we can tell from here actually that it actually included the user 9 order in that sub batch as well. So what I'm saying is that if we go back to here, okay, there's only one log stream, but it reused it twice. It reused the micro VM twice. This is the first execution of the micro VM, and that was all fine. This is the second execution of the within that micro VM, and in that batch was the user 4 order, the user X order, and the user 9 one. We don't see the user 9 one though because it has thrown an exception and it never got to look at user 9. I could kind of prove to you that user 9 is in there because if we expand this guy to look at the full event, and if we look at the body, let's see. Somewhere in here is going to be user 9. Let's try and just do a search for user 9. So we can see that user 9 was actually in that batch. Okay. Don't know if that actually makes sense to you now, but so uh, lots of interesting stuff going on there, though. The overall point anyway is that this DLQ is a mechanism for dealing with cases where your Lambda throws an exception while it's processing a batch, and you can kind of programmatically deal with the particular batch that it's trying to process. It doesn't sort of get lost. That exception doesn't get lost. This can also arise if the Lambda actually just times out. If you haven't allocated enough time for your Lambda to process a batch, when that happens, the Lambda service will interrupt the Lambda function. That's what we call a timeout. But it's the same kind of situation. It's an exceptional situation. And that batch of messages would be put into the DLQ as well. Okay, how are we on time? Let's just push on, I guess. So what I'm showing you in this set of slides here are uh, screenshots from this execution. So in my case, it did actually create two micro VMs running my process orders. This was logstream 1, and this was logstream 2. And this is which one contained the user X. You can see it there. User X. And this shows the log stream from the failed orders Lambda. Again, there were two parallel instances of that. So this is log stream 1 and this is log stream 2. It says log stream 1 there, but that should be log stream 2. And anyway, you've seen a kind of a live execution of it, even though it turned out very different, actually. It didn't create two parallel instances of either of my Lambda functions, presumably because the Lambda service was just too busy, I guess. Okay, so that's as much as we're going to look at in SQS. So what it is a messaging service. It's all about decoupling your compute components, which happen to be Lambdas in our case. Why we decouple, we've talked about that a lot. It's all about increasing or reducing latency, which is really about decreasing response time, improving latency, I should say. Um, Improving scalability as well, and we talked about that. Uh, we talk about producers and consumers in relation to SQS. We use different terminology when we look at another messaging service called SNS. The consumer is responsible for polling, that's okay. And the DLQ was all about dealing with error scenarios. In the lab, if I just switch over for a moment to the lab for this week, slightly different in that, do have a visual. What we actually do is we upload an image, a file really, to an S3 bucket. And S3 is actually the producer of the message. So you can get S3 to send a message to SQS whenever the state of the bucket changes. And you can be specific. The state change may be as a result of a new file or object, to use the S3 terminology. When a new object is added to a bucket, you can get the S3 service to generate a message and send that to an SQS queue. And then we've got a Lambda that's actually processing those messages. The message in this case will contain the name of the object and the actual bucket. So technically, this Lambda here could now actually read the object or the file that was uploaded to the bucket and process that, whatever that means in the context of whatever the content of the file was. So that's what you will do in the lab. Now, there are many other sections in this lab which I will add on later on from next week onwards. We just have a tiny bit of time left, and maybe what I'll do is start the next section or the next set of slides, which looks at another messaging service called the SNS service. So let's just start to look at those slides. So it's just another one of these kind of communications related services. And okay, again, it predates SNS, predates the whole serverless model. Although here in the second bullet point, I'm using the word serverless in its description, but like I say, uh, it does predate it. But in this case, SNS is what we classify as a publisher subscriber, or pub sub for short. It's a pub sub messaging service. SQS is kind of it's more of a point-to-point messaging service. That I didn't use that terminology back then, but SQS is all about sort of a producer wanting to send a message to a consumer. It's kind of a one-to-one type of relationship. Whereas with SNS, it's a one-to-many type relationship. It's where you want to send a message to many consumers and you want all of the consumers to receive that message. You cannot do that with SQS. If you've got multiple consumers for the same queue in SQS, only one of them will receive the actual message and process it. With SQS, you want all of your consumers to receive a particular message or set batch of messages. Now, we don't use the term consumer in the pub sub world. We talk about subscribers, but subscribers are essentially have the same general role as consumers. And we don't talk about producers of messages. We talk about publishers of messages. You may have come across this term pub sub before in other modules. So SNS is essentially, it's not a pub sub is not an Amazon term. It's a term that's used generically whenever you've got compute components that want to communicate in an asynchronous way, but you want this kind of one-to-many type communication between them. So it's when you want to send a message to many receivers, as I'm saying there. The publisher sends a message to an SNS topic. Again, topic is another term that we use in SNS. We don't talk about queues. We could essentially think of them as the same thing, really. But just to be accurate, we say SNS topics rather than SNS queues. So a publisher sends a message to an SNS topic, and you can have many subscribers. We talk about them listening to a topic for messages. And each of the subscribers will receive every message that's written to an SNS topic. The subscribers, again, it just doesn't have to be a Lambda. The subscriber could be an SQS queue, and we will actually see that in the labs. The subscriber could be an API gateway. That's what we mean by HTTP, stack HTTPS, or it could be a load balancer. Yeah. It could be an email server. There's a service called SES as well. It's all a bit confusing. SES stands for Simple Email Service. We will actually use SES in the labs later on. and it won't actually be, we won't use SES as a subscriber to an SNS topic. We will actually get a Lambda function to use SES to send emails to a destination. Also, SMS can be a subscriber. So essentially, like when you send a message to an SNS topic, maybe you want that to trigger the sending of an email or the sending of an SMS message. That's why these two can actually be direct subscribers to an SNS topic. From the publishing point of view, again, it's not just a Lambda that can publish messages to an SNS topic. You can get S3, and that's what you're actually doing in the lab, to be the publisher. You can even have CloudWatch. You can configure CloudWatch if you've got what are called CloudWatch alarms, something some of you may have come across in an earlier semester's module. We won't look at CloudWatch alarms, but suffice it to say that the publisher could be other types of resources other than just Lambdas. Obviously, we can use the CLI as a publisher as well, and that's we will do that in the lectures, actually, not in the labs. From a security point of view, encryption is built into the SNS service because SNS messages are obviously traveling across the network, and by default, SNS will encrypt those messages, and it will also encrypt the messages while it's holding them or saving them for a subscriber to receive them. The last point here, message filtering, is something that we will look at a lot actually in about 2 weeks' time. Sometimes you don't want a subscriber to receive every message that's sent to an SNS topic. You want it to be able to filter out particular messages that it's interested in. And the way we do that filtering, it can be quite tricky when we do it kind of at the CDK level, not at the subscriber level. We essentially associate the filtering with the topic itself rather than with the subscriber. So we'll see that in a while. It's the same kind of security kind of issues. The publisher needs to have permission to send messages to an SNS topic. The subscriber needs to have permission to receive messages from an SNS topic. So and that's all done via, or it's all done using the IAM service. Now, fortunately, because we're using the CDK framework, a lot of the IAM policies are auto-generated for us by the CDK. So that's fine. And also, you may want to allow you create an SNS topic within one AWS account, but you may want to make that topic available to publishers or subscribers that are linked to another AWS account, but you need to have the necessary permissions associated with the SNS topic and with the publishers and subscribers for that to happen. And scaling is built into it as well. Essentially, SNS scales up to any number of subscribers and any volume of messages. Finally, I'll leave it at this. There is this kind of DLQ feature available to SNS as well, but it doesn't work in the same way as it does with SQS. Where the DLQ comes in is where SNS is unable to contact a subscriber. What I should say actually is that in the case of SQS, the consumer polls SQS for messages. It doesn't work that way with SNS. With SNS, the SNS service sends the messages to the subscriber. The subscriber doesn't need to poll SNS for messages. Okay. But so SNS is responsible for sending messages to a subscriber. But if for whatever reason it cannot contact the subscriber, so if it's a Lambda function and the AZ zone that the Lambda uh, um, is available within, let's say that AZ zone is not is down, then that would mean SNS cannot contact the Lambda service to send the message. It'll obviously retry multiple times, but eventually it will give up. And in that case, it would send the message to a DLQ. Now we can't uh, kind of create that scenario where, let's say, if the Lambda is a subscriber and certainly the Lambda is not available, other than manually deleting the Lambda, I guess. But the DLQ is available to SNS for that particular kind of use case. Okay, I think I'm going to stop here actually, and we pick it up with a demonstration of SNS the next day. And having done that, then I will reveal the next part of the lab, which involves using SNS. Okay, I guess nobody's going to ask me any questions either about this or perhaps about the assignment. Are there any questions from you? No. Okay, I'll be present in the labs tomorrow morning as usual. That's fine. Thanks for staying tuned in if you are still tuned in. Bye bye.